pipe, pipe settings, the other things in the process industry. In the process industry, we use often so much of the pipe network, the pressure drop, the lot of amount of energy consumed is through the pressure drop. So how to estimate this pressure drop calculations, and for the required transportation of the fluids, how much power, what capacity of pump is needed, and those things we can also calculate using the DWC. So for example, let's just say, so today we will see pressure drop calculations, requirements, the pump. We can estimate these two using the process simulator. So for example, we have a storage tank. We have a storage tank where they have stored the raw material, and this needs to be pumped. This needs to be pumped to some other process. It could be CSTR, it could be another storage tank, or it could be reactor, or it could be distillation column or absorption column. We need to pump the fluid to that one. So in this line, we usually place a pump. We usually place a pump. So this is the inlet from the storage tank, and the pump is connected. And from this fluid will be transported. So here sometimes we use elbows, and we use bends. Sometimes we use valves. We use joints, connectors, many things we use in the typical process industry. So of course we have a simple pressure law or pressure drop equations available to us, but instead of the same expression, same methods can be used. Same methods, same expressions were used in DWSIM to calculate, or any process simulator, Aspen or HYSYS or DWSIM, anyone. In all process simulators, same thing can be used. So just making this piping network to give a visualization experience. So how to set these conditions in this process simulator? I just wanted to explain, so that in a process, because we wanted to more and more make it more industrial realistic. So what are all possibilities present in the industries we wanted to see and simulate that process. So this is one storage tank or one process vessel, and this is another process vessel, and the fluids are being transported from this process vessel to this process vessel using pump and pipe network, using this pump and the pipe network. So in this case, how much energy, what is the pump capacity is required? What is the power required for the pump? Because whenever we wanted to purchase a pump, we will say half HP motor or 2 HP motor or 3 HP motor. How much energy is basically what capacity the pump is required. If you want to select a pump, it primarily depends upon how much head it generates, like how much height this can send the fluid without any cavitation. So this is the head, like from the let's say this is the top point to this bottom point, how much head it can generate from the bottom to top, how much head it can generate. And so this is hydraulic head, how much head it can generate and what amount of power is required for the required conditions. These two are the important specifications for required pump. If you keep under low power pump or than the required one, definitely it doesn't meet the requirement. At the same time, if you keep a very high one, it will give a lot of flow rate. Again, you need to have a lot of control system to regulate it. So there has to be always some optimum value which we need to give for the pump calculations. So we wanted to simulate this process using this DWC. So let's say we will take some arbitrary values. Let's say this pump is 1 meter from the storage tank. From the storage tank to this inlet of the pump is 1 meter. Now let's say this is a half a meter. Let's say this is a half a meter, 0.5, and let's say this vertical pipe, the scale vertical pipe is, let's say, 50 meters, and so there's another 0.5 meters, and let's say this is 0.25 meters. Let's say this is the typical systems between two processes. It was like this. So how do we model this? How do we model this system? How do we model this pipe networking and pump specification system? This is very simple, but at the same time, it is very important to know what is the pressure drop, because pressure drop directly gives us pressure drop directly. Pressure drop means what? Pressure losses. Pressure losses means energy losses. Energy losses. If very high pressure drop means high energy losses. High energy losses means what? Basically, energy means energy is the operating cost of an industry. To operate industry, we need to supply the energy. So this is the operating cost of an industry. So more energy losses means more amount of energy we need to spend, and more amount of energy we need to spend, more and more amount of cost we need to give every day to run the process. So that's why the pressure drop is a very, very critical factor. Pressure drop is the very, very critical factor. So for example, if you use two-wheeler, suppose if you use two-wheeler, right, it has air filter. It has an air filter. Usually bag filter they will use. Bag filter. So this bag filter basically collects the particles in the air and sends the clean air to the internal combustion engine. This bag filter purifies the air, and sends particles free or dust free air to the internal combustion engine, IC engine. Now suppose, let's say you haven't cleaned this bag filter for a long time. The bag filter was not cleaned for a long time. So what happens if you don't clean bag filter for a long time? The bag filter get choked. Now it offers, the choked filter offers lot of resistance. For the fluid to flow. Lot of resistance for the air to flow. So if offering lot of resistance means lot of pressure drop. That means it is offering lot of pressure drop. That means it requires lot of energy for the air to flow. It requires lot of energy for the air to flow. So how that energy comes? Most of energy goes in terms of the whatever battery it is there, whatever fuel we are using, that will be utilized partially for the filter. And also, if you don't get sufficient of air, what will happen? Sufficient combustion also will not take place. So that's why pressure drop is very, very important, because pressure drop is indirectly relates to the energy losses. Sorry, directly relates to energy losses, and it indirectly relates to the operating cost of an industry. If we have a lot of pressure drop, then we need to have a lot of energy. So how much energy of the pump is required? That is also directly related to the pressure drop. We have a famous equation, Bernoulli equation. Bernoulli's equation. Bernoulli equation. Can anyone tell what is the Bernoulli equation? Anyone remember Bernoulli equation? Bernoulli equation, energy conservation equation. No idea. Delta P by density plus GH plus V square V square by 2 into density equal to energy losses due to friction plus energy supplied by the pump. If you have a pump, I'm sure you have seen this in your fluid mechanics book. So energy supplied by the pump is indirectly or direct relates to the pressure drop. If higher the pressure drop and higher the amount of energy we need to supply from the pump.
Sir,
Right. Yeah.
sir, we have already divided it by density, so there should not be one more extra density term in the.
Sorry.
Sir, we have already divided it by density, so in the third term it should not be, I guess, be half p square into density, because we have written delta p by density.
A half v square by 2. Yeah. Here no density term. Correct. Thank you. Yeah, no density term will be there. So thank you. So energy supplied by the pump is relates to the frictional losses, relates to the um, pressure energy and kinetic head and potential head. So the pressure drop, higher the pressure drop and higher the amount of energy we need to externally supply using the pump. So in a piping network, often we use valves, bends, T joints. So this sort of simulation required how to minimize this energy losses instead of doing a practical experiment. Instead of doing a practical experiment every time, we can simulate this process in a process simulator, and we can see which type of arrangement gives the least amount of energy losses, so that we can maximally optimize the system or we can minimize the operating cost. So that's why these calculations are also important, although these are very, very simple. Now, we have multiple formulas for laminar flow. Anyone remember what is the pressure drop equation we use for the laminar flow? Anyone remembers pressure drop for the laminar flow conditions? To estimate the pressure drop for laminar flow conditions, does anyone remember what is the expression we use? Hogan-Poiseuille equation, delta P viscosity mu VL by 2D. Velocity into length of the pipe by 2 times the diameter. So this is very important equation. This is only predominantly works for the liquids. Predominantly accurately predicts for the liquids. For turbulent flow, we have another expressions as a function of friction factor. We have a correlation for the friction factor for the turbulent flow, and delta P equal to 4 times friction factor into length into v square is 4FL square by 2D. So this is the friction factor. For laminar flow, F equal to 16 by RE. For turbulent flow, we have the different set of correlations available for the turbulent flow. And for turbulent flow, that also depends upon the smooth pipe. But however, these two are good for the fluids. Turbulent, this expression is valid for fluids. Now for the multiphase flow, it is more complicated. For multiphase flow, it is more, we have correlations for the friction factor, and so there's a little complicated, like we have a partially vapor, partially liquid. So if such of the thing, but all the three cases we can solve using the DWSIM. Different methods are available in DWSIM or any other process simulator to estimate the pressure drop. So let's see, we will just solve this one in a, so I will close this. So I will open new one. So we'll just solve with water. We'll assume that water is flowing from, this here to this storage tank. Water is flowing from here to this storage tank. So we will take water. As the feed stream. Now, what is the property package we need to use? What property package should I select for water? At least this should be answered by students. Yeah, anyone?
Sir, can you please show the dialog box on the screen?
Sorry?
Can you please show the dialog box on the screen?
This one?
Yes, sir.
So maybe I'll put it at the right place and you can guess.
So for water, like, can we use steam tables?
Yes. For water, we have to use steam tables. So, so we have material stream. So this is water inlet. So we're assuming it is at room temperature and atmospheric pressure, and the mass flow rate influences a lot in the pressure drop calculations. Mass flow rate influences the pressure drop calculation because it has a velocity term. Mass flow rate, mass flow rate influences the velocity, influences the pressure drop because mass flow rate influences the velocity, or mass flow rate directly relates to the velocity. For a given pipe, for a given diameter pipe, for a given diameter pipe, we have higher the mass flow rate, higher the mass flow rate, higher the volumetric flow rate, higher the volumetric flow rate, higher the velocity, higher the velocity, higher the mass flow rate, higher the velocity. So I'm keeping 1 kg per second. I'm just keeping 1 kg per second, which is default value here, but we can change. So we have to accurately keep this one here. So this one, this one. So this is the feed water going into 1 meter pipe, going into 1 meter pipe. So first going into 1 meter pipe. So you'll go to pressure changes. We have orifice plate, compressor, pipe segment, pump, and expander. Basically, this is turbine, and we have also valve. We have also valve. So we need pipe segment because we have the pipe. Now the pipe as an inlet is water inlet. Outlet stream is not there, so we'll create an energy stream. We have to create because if sometimes we can have a lagged pipe, sometimes we have an insulated pipe or which is lagged pipe. So at that time, energy stream helpful. Energy stream, having the energy stream helpful because if you see in the pipe segment, let's say pipe 1, pipe segment has general, hydraulic profile and thermal profile. So we can also make it like, we can also heated pipe, like, as the fluid is going on, sometimes we need to maintain certain temperature. And, so we can, I think while I explaining the P and ID diagram, I have explained, suppose we have a pipe and we have a pipe that needs to be maintained at certain temperature. That needs to be maintained at certain temperature. So that's called trace heated pipe. That's called trace heated pipe. So this is a pipe, and the fluid is flowing into this pipe, and this needs to be maintained at a certain temperature. So when the fluid flows, since the pipe is exposed to atmospheric air, and and because of the temperature gradient, the fluid might lose certain energy. The fluid might lose certain energy. One way is you can keep an insulating pipe, and you can control the temperature. And another way is you can also have the traced heating. So they will simply uh, put an electric coil. They'll just put a simple electric coil through this, and they will give some power input, and that coil basically converts the electrical energy into thermal energy, and that heat is being transferred to the fluid inside the pipe, so that way it will maintain the temperature. So this is called trace heated pipe. So you can have insulating pipe, you can have a trace heated pipe, or you can have a pipe without any heat transfer. So this pipe segment requires the energy connection because this includes hydraulic profile. It also includes the thermal profile. That's why they have this energy streamline. If you are not worrying about tracer heated pipe or insulated pipe, we don't even define anything. We can just leave it as it is. We can just leave it as it is. So in the general guidelines, it might ask what is the outlet pressure and what is the outlet temperature. That calculates according to the pressure drop expression. Now, pressure temperature tolerance and pressure tolerance, like while calculating, how much error is allowed. Minimum error is allowed. So for since pascals, 1 atmosphere equal to 10 to the power of 5 pascals, we'll keep the pressure tolerance as 100. And temperature is 1 degree centigrade, is also matters, so the tolerance value is keeping by default, it keep it as 0.01. That is basically for the iteration point of view. Now here pressure drop correlations, we have Beggs and Brill and Lockhart and Petelas and Agis. Multiple correlations are there. Beggs and Brill is primarily used for the liquids. But if we have multi-phase flow, we can use other two correlations. And we can use other two correlations. So since we're dealing with water, we'll just keep Beggs and Brill correlation for this one. If you wanted to have emulsification effect, you can also include the emulsification effect. Suppose if you are transporting crude oil along with water, along with drilling fluid, it will form an emulsion because of the presence of the salts. And so at the time, if you want to include the emulsion effect, we can also include the emulsion effect while while the fluid travels through the pipe. So this gives a lot of information, a lot of things which helps you to calculate it in a simple and easy manner. Now in the hydraulic one, we can define it as a straight tube, and multiple options are there. This can be a straight tube, and this can straight tube. This can be elbow of 90 degree, elbow of 45 degree, and elbow of 180 degree, and it could be angle wall, butterfly wall. It could be ball wall, gate wall, globe wall. So many walls we have. All the walls are actually being defined here. Check wall and T joints. Now we have the T joints. Now we have the quick reduction, sudden enlargement, sudden decrease. That is also there. Like one pipe is there that's being enlarged to bigger pipe, like venturi meter. Like venturi, we can define it as a venturi. Quick reduction, border inlet, normal inlet, quick expansion. All types of possible combinations are given in this hydraulic settings. We can define it whatever you want it, whatever you want it. So I'll initially, since it is I keep it as a straight tube, so I'll define it as a straight tube. I'll keep it as a straight tube. Now how many? Only one quantity. And the materials of construction. What type of material is carbon steel, cast iron, stainless steel, or PVC pipe? If it is and commercial, whatever commercial copper pipe, we can select any one. So I'll just take it as a carbon steel pipe. So by default, it will have certain roughness, and that gives the roughness value. And length, we will need to define. The length is 1 meter. Length is 1 meter. Elevation is 0. This is horizontal pipe, so elevation is 0. And external diameter. So for external, when you double click here, you can enter the diameter or you can double click. And these are the standard pipes available. These are the standard pipes available. So 1-inch pipe, 2-inch pipe, 3-inch pipe, almost up to 16-inch pipe. We have the standard pipes we have. Now in the pipe also, we have different schedule numbers. We have the different schedule numbers. Those schedule numbers determines the what thickness the pipe should have. The schedule number gives us the what thickness pipe should have. And the higher the schedule number and higher the thickness of the pipe. So for example, if you see here, schedule number 5S. 5S means the schedule number is 5. If the schedule number is 5, the inside diameter of 1-inch pipe with 5 schedule number is, outside diameter is 1.315 inches and inside diameter will be 1.185 inches. You can see outside diameter is constant. The 1-inch pipe means the outside diameter is constant. But depends upon the schedule number, the inside diameter varies. The higher the schedule number, the lower the inside diameter, because the thickness is the increases. If the schedule number is higher, the thickness of pipe increases, the inside diameter decreases. So 5S will have 1.185 inside diameter, 10S will have 1.097 in the inside diameter, 40S will have 1.049 diameters. So this is schedule number is basically, if you want to select a pipe, we need two things. One is what diameter of the pipe you're looking for, and what length of the pipe you're looking for, and what is the thickness of the pipe you are looking for. So those things matters. So I'll just commonly we use 40s. Commonly we use by default, you will use the 40s is the common required thickness. But of course, that depends upon what fluid is going, what pressure losses, and how much stress the fluid offers on the pipe. Everything matters. So I'll just take 2-inch pipe with 40s with the 40s. As soon as you select it, you will get the inside diameter and outside diameter in millimeters. It will be calculated. It will be calculated. So now this is the pipe one. This is the pipe one. Now after the pipe one, I need to introduce pump. I need to join a pump here. So I will drag and drop down the pump. So this is the pump. So this is the pump. So pump again have inlet stream. So the stream 3 is going to the pump. So stream 3 is going as inlet to the pump. Outlet stream I will have to create. Energy stream I will have to create. I will have to create. Now the pump is primarily used to pressurize the liquid. Pump is primarily used to pressurize the liquid, or it can create some pressure head so that the fluid can go to higher elevations. So we can have multiple options. We can set this required outlet pressure. We can also use to estimate the power required, and we can also generate the performance curves for a pump. So we'll go for the certain outlet pressure. We'll go with the certain outlet pressure. So this pressure is certain outlet pressure, whatever. Let's say initially I'll keep as 3 bar pressure. I will explain you what is the need of this pressure afterwards. 3 bar pressure. 3 bar pressure. Efficiency we can take an average 70%, but that varies, and that we can get it from the that from for this efficiency for this pressure head we can use performance curves to find out what capacity the pump is required. Also, we can calculate from this one. Now, from this pump, we have another pipe segment which is of 0.5 meters. So I'll just put the pipe segment here. This is again at 0.5 meters. So inlet to this one will be 6, and outlet is stream is created, and energy stream. Again, why we using energy stream? Because I just explained we can have trace heated pipe or insulated pipe, depends on the requirement. Now we have another pipe which is of 50 meters, so I need another pipe here. So we can have 2 pipes, or we can have 1 pipe, then we can define it as a 2 pipes. Both are possible. Both are possible. Both are possible. So I don't want to create too many pipes. So this pipe can be defined in this one pipe segment only. Can be defined in this one pipe segment. So let's see how does it looks like. So this is the standard. I just explained this one. Now, if you go to hydraulic profile, we have first of all, we have 3 things. First of all, we have a strike tube. Then we have another pipe with certain elevation. Then we have another pipe with horizontal pipe. Then again, we have a pipe with certain elevation. We have a pipe with certain elevation. We can define all the 4. 1, 2, 3, all the 4 at one go. All the 4 at one go in this one pipe segment. So we have strike pipe, we have quantity 1, then we have we'll select again carbon steel, then we have the length, we have length 0.5 meters, 0.5 meters, elevation is 0, and again we select 2-inch pipe with schedule number 40. Then we can add here, we can add another segment. We can add another segment. Multiple segments can be added. This is the segment 2. This is again a strike pipe, but with elevation of 50 meters. With an elevation of 50 meters. So I will again select carbon steel. Carbon steel length is 50 meters. 50 meters. Elevation is also 50 meters because height of this one is also 50 meters. You can see 50 meters is the elevation. Now again, we'll select same thing, 2-inch pipe with 40 schedule number. So I have first I have defined this. Now I have defined this. Now I'm going to define this. How I define it? I'll just click in add segment or add section. So I'm doing the third segment here. Now I have the third segment here. So I'll select again carbon steel. Select again carbon steel. So length of this third pipe is again 0.25 meters, 0.5 meters, and elevation is this in horizontal pipe. So this is 0, and external diameter is 2-inch, and again I'll take the schedule number 40. So when I taught this process equipment design, at the time I showed you how the schedule number. I hope you also, I think I didn't teach you guys, maybe I taught your seniors at this pipe calculations. So now we have the last one. This is 0.25 meters, elevation 1. So we have fourth segment. So again, we have the fourth segment. This is strike tube. Again, we select carbon steel. Carbon steel. Length is 0.25. Elevation is 0.25. Sometimes this length and elevation varies. Sometimes the length and elevation varies. At what case it will vary? Suppose the pipe is in, suppose we have a pipe. We have a pipe. I'll just take this pipe. Let's say this is the pipe, and this is in this with certain angle. This is with certain angle. Now for this case, length is, let's say the length is 100 meters. The length is 100 meters. Depends upon the angle of inclination. Angle of inclination, the elevation varies. The elevation varies. So the elevation is varies. So the elevation varies, and that depends upon the angle of inclination. So let's say this the width for a given elevation angle, let's say this is 50 meters. So at that time, if you want to, if let's say the pipe is inclined like this, then we have to define length is 100 meters and elevation is 50 meters. Length is 100 meters and elevation is 50 meters. So for inclined pipes, both varies, but for horizontal and vertical pipe, these are very simple. That is very simple. So 2-inch pipe, and I'm taking the schedule number 40. So now we have defined segment 1, this is segment 1, segment 2, and segment 3, and segment 4. All the 4 we have defined. Now the water from this inlet is going to this tank. So we have separated some tanks, and we have the tank here. We have the tank here. So the tank has one inlet stream. So that is stream number 9, and one outlet stream which is going out. We have this one. Now the tank volume we need to specify. Let's say this is 15 meter cube or 10 meter cube tank, whatever randomly we can give, because we're solving the general problem. So now we have defined whole process from this point to this point. We have defined the whole process. So if I solve the flow sheet, sometimes it can give an error, sometimes it may not give error. So we have to see what is the pipe 1. So hydraulic profile is not set. So okay, yeah, hydraulic profile is not set. So we have to select carbon steel, and length. Let us see. Initial length is 1 meter, and elevation is 0, and external diameter is 2-inch. So we have defined this. Now let's solve the flow sheet. What's happening? Length 1 meter, elevation 0 meter, 2-inch. Yeah, now probably again. Okay. Oh my god, I didn't click press. Okay. Yeah, mistake. So I'll do it again. Sorry. Meters, meters, 2-inch, 40. Then we have third one, 0.5 meters, 0. Elevation 0.25. External diameter is this. Yeah. So now we have defined. Maybe now we can solve. Yes. So now we have defined. Now we have defined. Then I run the flow sheet. Now I run the flow sheet. Now it is giving an error. Like here, let's say this is pump, and error is coming out of the pump. The error is that a negative pressure was calculated inside the pipe segment. And the error was raised in calculation. So negative pressure means what? Inlet pressure is lower than the outlet pressure. Negative pressure means negative pressure drop. So inlet pressure is lower than the outlet pressure. That means I have set to the 3-bar pressure. I have set to the 3-bar pressure. So this is not sufficient. This is not sufficient. The pump is not sufficient to reach to the top level. This pump capacity, whatever outlet pressure I'm giving, is not sufficient to reach to this water level. So I need to increase higher. Let's say 4 bar. Let's say 4 bar, and we run the flow sheet. So again, a negative pressure was calculated inside the pipe segment. Now we'll go for 5-bar pressure. We'll go for 5-bar pressure. So now it is coming. It is whole process. Whole flow sheet is got solved now. That means the pressure is sufficient now. Whatever pressure we are giving with whatever pump, the pressure head which is generated by the pump is sufficient for the fluid to reach this tank, or sufficient for the fluid to reach this tank. So now from the water can flow from water inlet to this outlet or to this tank with this required pump. Now if you wanted to select a pump, if you want to select a pump for these conditions, for this set of conditions, you need to select a pump that should have capacity higher than 0.54 kilowatts. 0.54 kilowatts. If you need a pump for this process, if you want to design a pump or select a pump for this process, you need a pump which having the power requirement of 0.54 kilowatts. 0.54 kilowatts, assuming that the pump is functioning at a efficiency of 70%. If the efficiency decreases, we need the whatever power required will be increases. The power required will be increases. Now, uh, we can also find out that for this flow rate, for this mass flow rate, 1 kg per second, with this pump, you can fill this tank in 9969.67 seconds. 9969.67 seconds. It's almost like takes 3 hours, close to 3 hours of time. If you're introducing water at this flow rate, 1 kg per second, and if you use 0.5 kilowatts power pump, this tank will be filled in 3 hours time. Now this residence time also matters, in CSTRs and PFRs, the residence time matters a lot. So you can also you can also calculate if I wanted to maintain the residence time here in only 10 seconds, what flow rate I need to send and what capacity the pump is needed. We can always calculate. Let's say whenever we wanted to have a set, whenever we wanted to go for a desired set point value, we know that we have to use this controller block. We need to use this controller block. This control block gives you what you want to manipulate to achieve the required set point value. What you want to manipulate to achieve the required set point value. Let's say the manipulated variable is the residence time in the tank. So tank is 11. Here the tank is 11. The manipulated property. So manipulated property, sorry, that is the set property. Manipulated property will be the water inlet. Manipulated property is water inlet. And what we can vary? We can vary mass flow. We can vary the mass flow. We can vary the mass flow. The current mass flow value is 1 kg per second. And what is the controlled object? What you want to control? And 11, that is the tank. 11, that is the tank. And control properties residence time. Or you can have liquid level, you can have pressure, or whatever you want to manipulate, you can manipulate. I'm just showing here one example of residence time. So converge, and you can say, let's say I wanted to fill this in only 3000 seconds or 3600 seconds. I wanted to fill in 1 hour. Let's say I wanted to fill in 1 hour, so I can give the set point value 3600 seconds. Then we can run the flow sheet. It does all the calculation. So now it is saying that the negative pressure was calculated. That means we have increased the flow rate. The pressure is not sufficient, so we need to have the higher capacity pump. When you want to speed up it, we need to increase the flow rate, and we need to also increase the pump capacity. So let's say we will keep, for example, we'll keep maximum as 10 bar pressure. Then we run this flow sheet. Oh, so that's not sufficient. So we'll keep 15 bar. Still the negative pressure is occurring. So still negative pressure is occurring. Yeah. So this way we can play around with changing the flow rates, changing the residence time, changing the outlet pressure. All the variables we can vary. Negative pressure is occurred, so we'll go with higher pressure. Yeah. So initially we have 1 kg per second. Now it's gone to 51 kg per second. So obviously the pump capacity increasing. And it's not realistic to have 100 bar pressure, but I'm just showing you what is the possibility. Okay. So 150 bar pressure, 100 bar pressure pumps definitely will not be there. And also 1 kg per second itself is a huge flow rate. 1 kg per second is it's almost like 3,600 kg per hour. So it's a huge flow rate. So that's why I have taken the unrealistic numbers. If I have to handle that, then I need to have a bigger pipe. I need to have a bigger pipe. So maybe I will set this as, oh, set point is 1 second it took. What's happening? No. Um, let's say I'll delete this. I don't know why this adjust function yesterday also gave trouble. Today also gave the trouble. Yeah, so this is done. Let's see residence time. It's coming to be 9969. Let's say since this adjust function here, adjust function, manipulate object is water inlet, mass flow 1 kg per second, controlled object is 11, that is time, and the residence time. Let's say I wanted to reduce this to set point value of, let's say, 9,000 seconds, and let's say run the flow sheet. Yeah, so I have reduced from previously 9,999 seconds to reduce to 9,000 seconds, and the water inlet is changed from, just 1 second. Sorry. So now previously it was residence time of 9,900 seconds. Now when I previously went from very high value to low value, so it is giving an error. So I have reduced to very small number, 9,999 to 9,000 seconds. So the water inlet flow rate is varied from 1 kg per second to 1.107. So this way we can understand understand we can also do sensitivity analysis. Earlier I showed you how to do adjust function and sensitivity analysis parallelly, or both gives actually similar information and message. So this way we can understand for a given flow rate what capacity of the pump required. Now we see the capacity of pump is 0.59 kilowatts. So for a given process industry, depends upon those needs, we can easily do this pipe settings and calculate, and we can understand how one varies, how everything else vary. A lot of information we can extract from this using this process simulators. Using this process simulator. Now, in this pipe segment, here, whenever here, I just put as straight pipes. Like we have a straight pipe here, we have a straight pipe here, we have a straight pipe here. But whenever there is a bend, whenever there is elevation, whenever there is a horizontal vertical pipe, we always have we always have a bends. We always have a bends. So the bends are uh, these are the typical bends we use. So this is the typical bend we use. So instead of a smooth or immediate this one, we will use this type of bend. Now depends on the angle, the bend varies, 45 angle, 90 angle, and sometimes there's also we'll also use elbows. And here one bend, here another bend. So bends will offer more resistance and more energy losses than the straight pipes. So we can also add bends here. Suppose we have a bend here, we can add a bend here. Like we have this pipe segment in the hydraulic profile. So we can add a bend here. So straight pipe, we can add a bend here. So if we go to fifth one, we can have a elbow of 90 degree. The bends is defined in the here as a elbows. So 45-degree elbow, 90-degree elbow, and 180-degree elbow. So right now, let's say this is 45 elbow, and the quantities are 1. Uh, Now we can have again same materials of construction is carbon steel, The length of the bend, what length we using, how small, how big. So let's say this is very small. So come on, nothing is coming up. I don't know. Somehow it got hanged. We just simply enter length value, elevation value, external diameter, internal diameter, the way we have done before. So just by that way we can reduce elbows, and as I said, we can reduce many walls, angle wall, butterfly wall. We have various types of walls, And valves also offer a lot of pressure drop, a lot of resistance. It will also generate a lot of pressure drop. And so we can add multiple things. We can add multiple things. Um, we can add multiple things in the process so that we can understand the energy losses or pressure drop offered by these segments present in this piping network. So I hope you understood. Now, when explaining, I'm only showing small parts, important parts, because to cover each and every minute detail, it takes a lot of time. But those are all similar, so you all can practice it and we can understand it. If you face any issue, we always be welcome and we're happy to take your questions. So that's why suppose yesterday, Serendipity Exchange, I explained all the details. Now, each and everything I don't need to drag and drop down and show it to you. You can practice it. This because it's the same. It doesn't make any huge difference. I have given the conceptual understanding. I have shown one example. Now it is up to you. Like if you want to learn more, you need to practice it. You need to practice it. Then you will get a better and better and better understanding. So I hope you understood. If you have any questions, I'm happy to answer on this piping network. So I have only showed pipe segment and pump. Similar compressor is same. Compressor is used for gases and expander using the high pressure stream to generate power. We use the expander or turbine. And again, we can use valves, control valves we can put in the piping network. So that way, these are all similar features and you can explore. If you get any doubt, we are happy to answer to you. I'm happy to answer to you. So we covered pressure changes, then we have covered the separation tanks, then we have covered the mixer streams, then we have covered the exchangers, then we have covered the reactors, then we have covered the columns, right? And this is simple filters. This solids has very less functionality in the modeling and simulation. This is a simple sieving analysis. It's only based on the sites classification. So that's why I'm not explaining this because it doesn't give any good information on this one. Then we have discussed about the logical blocks. So I have covered maximum portions of this maximum topics in this DWSIM. Of course we have a few more details, and instead of exploring that, since I have another let's say 5 hours, I guess. Yeah, I have another 3 hours. Yeah, I have another 3 hours that is there in the next week. I wanted to show you all these things in Aspen. I wanted to show you major portions of this 3WSIM in how to run this in Aspen in the next week. So I will want to cover one more topic after that. Before that, I wanted to show. So next week I have fourth and fifth. So I wanted to show you Aspen. I wanted to show you the whatever we have done, like pressure changes, separators, mixer splitters, exchanges, reactors, all the things, whatever we have done in this DWSIM, same thing can be done in Aspen. Aspen is the most commonly used process simulator, and why the reason for not teaching directly in Aspen is you all, some of you are in home, some of you in the hostel, and we cannot install or we cannot. This is the open source software DWSIM, whereas Aspen is not an open source software. That is licensed software, proprietary software. So that needs to be installed specifically in specific computers. So because of that limited access, I haven't directly taught you in Aspen. Rather, as DWSIM is simple, you all can install, you all can practice, you all can explore. The interface is almost similar. So that's why I have explained in the DWSIM. One important concept apart from this unit operations is defining the crude assays, petroleum assays. Suppose this is the wow. Yeah. So students, I'll just take some water then I will continue. So you all also can take water. So we'll start after 4 minutes. I will continue the discussion after 4 minutes. So meanwhile, if you have any questions, you can also uh, think about it and you can ask me. So I will just come back after 4 minutes. I will just drink some water, feeling so thirsty. Yeah, thank you, students, for waiting. You got any questions to ask me on this, whatever we discussed so far? So the next one is crude essays. They call crude essays. Probably, uh, have you heard about true boiling point curve in CPT? Sir taught you. API gravity. In CPT, have you heard about true boiling point curve and API gravity?
So we know a little bit.
Okay. So of course, yeah, in CPT we'll teach less, and this called petroleum refinery engineering. That's an elective. that is exclusively more details of this will be learned. So API gravity. What happens in crude assays or crude oils? Crude oils. Crude oils are drilled from the petroleum reserves, then desalted, as soon as coming from the in the top surface, desalted. This crude oil contains lots of components, lots of compounds, lots of components. So it is predominantly hydrocarbons. In the hydrocarbons, we know that is C and H. Now the carbon number varies from C1 to 47. C1 to 47. Even then, it's not like alkenes only. It will be a combination of alkanes, alkenes, and alkynes. Alkanes. So huge number of components, uh, were there in these hydrocarbons. Now, if you want to define, let's say I need to define a crude oil properties. Define a crude oil properties in a process simulator. You know how many components you will select: propane, ethane, methane. You will have to select all the components, which is almost impossible to define what fraction of propane is there, what fraction of methane is there. It is very, very difficult to separate them into individual components or define into individual components, right? So, so the definition of crude oil properties are slightly different, and that come from this true boiling point curve or TBP curve, TBP data or TBP curve. So what they do in the true boiling point curve or differential distillation curve, there are two things: differential distillation curve. You will get in crude oil, if you do distillation, you will get pseudo components. You will get the pseudo components. Those pseudo components could be gasoline, pseudo oil component could be diesel, and gas oil could be kerosene. These are all pseudo components because we cannot define exactly what components are defined. We can only say it vary from C3 to C7 or C10 to C13. That way we can only give the range of this one. But we can say predominantly linear chain hydrocarbons or branched chain hydrocarbons are there. Like that we can only tell. So these are the pseudo components. These are not the, of course these are the products, but these are the pseudo components because these are not the, we cannot actually define gasoline in any process simulator. We cannot define diesel in any process simulator as such directly. So for this reason, they have the separate way of the defining this one. So in the true boiling point curves, what they do, probably you know this experimental procedure, uh, TBP setup. Let us say TBP setup. Something else. Okay. True boiling point curve. Yes. So this is the what you have seen in simple batch distillation. We have done in our mass transfer lab recently, right? You all have done mass transfer lab recently. So this seems to be a good image. Form picture. Yes. No. So what they do is they take crude oil in a round bottom flask like this. The number 15 is the crude oil, and they heat it to they heat they heat this crude oil liquid. Sometimes they heat they will keep a heating element, heating mantle. They'll cover it, or sometimes they can also place it under oil bath. They place it under oil bath to get the uniform heating rate. So, what happens is that once the vapors, sufficient amount of vapors travels through, so vapors will form inside, or let's say, yeah, after reaching the sufficient temperatures, vapors will form. The vapors will go and touches this thermometer bulb and comes to this one, and this is the condenser. These are the vapors. So during here condensation will takes place. During here condensation takes place. The condensate droplets are falls down here. The condensate droplets are falls down here. So what they simply do at zero, at 5 to collect 5% volume. Let's say it's volume getting collected. The volume of the condensate they collected here. The volume of condensate collected here. To reach 5 ml, of condensate. So this is the condensate volume. Condensate volume. How much, what temperature it required. When it reaches 5 ml condensate, what is the temperature indicated here? What is the temperature indicated here? So let's say the temperature is something like 300 Kelvin. 300 Kelvin. Now to reach 10 ml, what temperature? Let's say 350. So this is called the true boiling point curve. So the percentage, this is basically, instead of expressing in terms of individual volume, they express in terms of percentage volume of, or percentage vaporized. They'll convert into percentage vaporized. So the total volume of crude oil. Now we got the 5 ml of condensate. So 5 ml by the total volume gives the percentage. So this is called the true boiling point curve. This is called the true boiling point curve. So if you plot a graph between, let's take a typical TBB data, TBB true boiling point data for a crude assay. So this is the typical any TBP data. Okay, this is the typical TBP data. So cumulative volume collected. Let's copy this. Let's copy this and see here. Now here, from between 22 to 60 degrees centigrade, 2.49 volume of vapor 2.49% is got vaporized or condensed. Between 60 to 80, 5.02% of this is got collected. 80 to 90, this much is collected. Like this, we get as the temperature ranges, we get this percentage amount of crude oil got vaporized. Percentage amount of crude oil got vaporized. Now for each sample, they also measure the specific gravity, and they also measure the molecular weight. They will also measure the molecular weight. Now, what we understand from this is a pseudo component having the cut range, let's say 120 to 140. So from this we can know, let's say we know this gasoline cut range. We know. Gasoline cut range we already know. And from this gasoline cut range information, we can know in this crude oil how much amount of gasoline can be extracted, how much amount of diesel can be extracted, and how much amount of kerosene can be extracted, and so on. So that way, this TBP data will also gives you from this crude oil after distillation or after refining, what are the components, how much volume of pseudo components like gasoline, diesel, kerosene can be obtained. We can also get that information. So, whenever you do the this petroleum essays, the crude oil essays, we can go to the settings. Then here you can start distillation curve for petroleum characterization utility. Start distillation curves for petroleum characterization utility. So if you click this, you go to the new wizard will be open. Now here we can generate this assay curves based on the tree boiling pen data or differential distillation with no reflux, differential distillation with no reflux under vacuum, and the simulated distillation. We can use any one method. We can use, I just explained only TBP and differential distillation. We have also seen that in mass transfer lab. So differential distillation with complete reflux, differential distillation no reflux, both we have seen. Both we have seen, and I think recently only have done mass transfer lab, so you know it. So we can get molecular weight. Let's say we can use here. We have the molecular weight, specific gravity, and TBP data. So we have the molecular weight and we have the specific gravity data we can give, and we don't have any kinematic viscosity. Bulk sample API gravity, overall crude oil API gravity, and molecular weight we can give. So, and here we can copy experimental data, the percentage vaporized, the temperature, and molecular weight, and specific gravity of that one. Then it is basically plots the graph. In the step 3 from the data, it plots the graph and it measures the estimated properties. So instead of whenever you want to import a crude assay, instead of selecting components here, because we will not have gasoline, we don't have gasoline, kerosene, because they are not individual pure components. Instead of selecting components here, we need to define the crude oil properties in this way. We need to define the crude oil properties in this manner. So that is the different way of selecting the components. That is the different way of selecting the components for the crude oils or crude assays, right? So there are there are another way of also giving the crude distillation. We can give overall TC, PC, and all those things variables. That is more complicated, and the TBP data is more easy way to give the define this petroleum components. That is called petroleum characterization. So if you want, I can also show you. I will just give this data: temperature, percentage cumulative volume, percentage. So let's see what way percentage vaporized in temperature, percentage vaporized temperature. I just simply create copy paste this data here. That's all. Nothing. Once you copy paste the data, and if you click on the next, it will plot the data. Then it takes as a input. It will takes as a input into the DWC. It will takes as input to the DWC. So that way, even this crude assays, and very complicated petroleum components can also be defined using this process simulator. In this process simulator. So I hope you understood. If you want, I can also do that and show to you. What do you suggest? Will you do it or do you want me to do it? Okay, no answer. So let me show you specific gravity and molecular weight. 2.49, 5.02, 8.09, 11.14, 14.93, 18.92, 23.07, 26.97, 30.59, 34.48, 38.53. That is the percentage paper, and I'll take the average of the temperatures. I'll take the average of temperatures. So 40 and 70 and 90, 110 and 130, 150. I'm just taking the average temperatures. 107, 170, 190, 190, 210, 170, 190, and this is 110. So 210, 230, 250. So these are the temperatures, and specific gravities not given. 0.6755, 0.7052, 0.7242, 0.7421, 7571, 7745, 7838, 7931, 0.8020, 0.8178. Molecular weight 76, 93, 03, 113, 124, 134, 149, 169. So we'll take an average value between these two, 84.5 here. Here the difference between these two is where I just completed the data set. 6458. Yes. So now I can go to DW same previous molecular weight, specific gravity. So I know these two only. I know only these two. API gravity of this. So this is the Saudi Arabian crude cuts. Now I wanted the API value of this. What is the API gravity? Login API gravity. Let's just take API gravity and molecular weight of. So I'm just taking 38.50. I'm just taking some random numbers. 38.5. Not there. So I'll just take average of this 127, and this data I can copy from here. Placement report. So I have copied. So vaporization, percentage vaporization, temperature, molecular weight, and specific gravity. Now this is the TBP data, how the molecular weight varied with the percentage vaporization and how the temperature varied with respect to paper and percentage vaporization. Just whatever data we have given, this is plotted. And number of pseudo components, we can specify to be 7 or whatever. Let's see if we by default it shows 7, but we can vary. Now, if you wanted to get 7 pseudo components from this, if you wanted to get 7 pseudo components from this whole thing cuts into 7 segments. The whole thing cuts into 7 segments, like you can see 1, 2, 3, 4, 5, 6, and 7. 7 segments. So first cut could be in this range. Second cut will be in this range. Third cut will be in the range. That way, based on the number of pseudo components we are interested in, from this TBP curve, it will define what is the average boiling point value of that pseudo component value. It will give. It will give. Now, what are the methods we can use for the correlations? So we can use, these are the default and standard correlations we can use. Now it will give us the all the properties, TC value, PC value, AC factor. We can, for all these cuts, individual cuts, all the individual 7 cuts we have defined for the 7 cuts. For all the individual 7 cuts, it gives the all the property, viscosities and critical pressure, critical temperature. All these things can be, all these we can have it. Then you can say finalize it. So quality, like molecular weight, and this is the API value. This is the normal boiling point value. It gives this one. So this way we can define, now we can define the components. This is component. Now we haven't taken proper property package. So we have taken steam tables property package, but for the petroleum components, the best package is Peng Robinson property package. We can add it here. Then it will calculate properties very well, properties in the better manner. So this is the way, if you wanted to define, oh, it's gone. If you want to define a petroleum assay, we need to import this manner. We need to import, we need to define, and instead of defining individual components, we can define whole assay in one go. We can define whole assay in one go with help of this TBP data, true boiling point data, with help of this true boiling point data. Actually, this TBP data will be supplied. We can also do in our lab, and it will also be supplied by many of the research labs available across the world. And if we give the crude oil, they do this simple distillation and they measure this one, and they will give it. Instead of defining individual components, which is almost impossible, instead of defining individual components, the crude oil will be defined with help of this TBP or differential distillation data. Differential distillation data. So I hope you understood. Now we can see. Now we can see that this is the oil stream. Now this is the oil stream what we have created. So previously we have the methyl stream as water inlet. Now when you want to create water inlet, definitely we can select it from the components. But if you want to use crude oil, we cannot select it as individual components. Rather, we have to define as a crude, and that way we get this whole the thing. Now we can see the components. These are the cuts. These are the 7 cuts which is present here in this crude oil. And these are the steam conditions we can vary, we can give input. Now we can do distillation or we can do reaction or whatever. Of course, we want to reaction in this one. But of course, we want to do hydro treating and other things. We can do even reaction, we can do combustion, we can heat it. So for all processing, if you want to process crude oil, we cannot define them directly using this one. We cannot directly define using this skeleton because this is not a single component. This is combination of many components. So because of that, we need to define the oil stream or crude oil stream using this TBP data. Using this TBP data. I hope you understood. Guys, do you understood how to define the crude assay or crude oil material as material stream? You understood or not? How to define a crude oil or petroleum assay as a material stream? Is it making sense, or do you want me to explain or again so that you will understand better? So maybe I'll repeat. Suppose we wanted to do distillation of a crude oil. Now we will not be able to select crude oil because crude oil is not available anywhere in this material stream. Why crude oil is not be available here? Because crude oil is a combination of many hydrocarbons. We cannot define them as individual components. So since we cannot define them as individual components, we have to define separately. We have to define separately. We can define with help of either TBP data or differential distillation data or differential distillation with vacuum data or simulated distillation data. Any one data we can use, and these are the ASTM standard procedures. These are the ASTM standard procedures. If you want to go in detail, you can just Google search ASTM D2892 or D86. These are the standard methods. If you go to that, you will understand. And this TBP data, ASTM D2892, I just explained how we do. In D2A ASTM data, in the procedure, we take the crude oil, we heat it with certain heating rate, then we collect the condensate. Amount of condensate collected per total crude volume gives the cumulative volume percentage. Now collect to that temperature, to collect certain amount of condensate, how much temperature, what is the vapor temperature? So for example, for a vapor temperature ranging from 20 to 60 degrees centigrade, this much amount of condensate percentage of this much percentage volume of condensate is collected, and the specific gravity of that and molecular weight of that fraction is given. That way, they heat it up to a very high temperature, almost up to 260 and 300 degrees centigrade, and they collect it. They wait till the max amount of condensation takes place. Till the max amount of condensation takes place. With help of this data, we can define the crude assay. With help of this data, we can define this crude assay. So I just took this data available in our from a journal paper. I also showed you, and that one I have just typed here. And this data I have imported. This data I have imported, and I have given the overall bulk API gravity molecular weight. then I have copy pasted here, then I just processed it. Then once you process it, it will appear as a string. It will appear as a material stream. Water stream, ethanol stream, that is very simple. You can straight away define it in the selecting the components. But crude oil is not a one component, it's combination of many components. So we have a pseudo components present there. So we have to use crude as a tab to define the petroleum essays, to define the petroleum essays. So I hope you got an idea. Maybe if you practice and if you just revise some of the concepts in CPT or petroleum refining engineering, you will understand better. So with that, I have covered general material streams and crude assays and mixture of the components. We have seen multi-component system. Then we have seen all other unit operations available in any process simulator. We have seen all other available process simulator available in this stream. Oh, I think one student asked me to explain the absorption column since already 9:50. So I will explain that in the next class. So next class I will explain absorption column using this BWSIM. Then I will show you how to do this in Aspen, another process simulator, another software that I will do in the next week Monday and Tuesday. So with that, I think this semester is finishing by 5th. So I will explain. I will try to complete because since I already explained in the DWSIM, it is very fast to show in Aspen. So on 4th April and 5th April, I will show you all these calculations with help of Aspen. And you have this Aspen lab or Cape lab in the next semester, where again you will practice with help of Aspen anyway. So it won't be any issue. So you will get a very good understanding. And as I announced in the last class, we will have test on 12th April. We have test on 12th April, not 5th April. So that's all from me. If you got any questions, please let me know. I don't know. When I ask questions, you guys don't respond. When I ask questions, you don't ask any questions. What's happening? I don't know anything. Also, very shocking. So only 10% or 20% students are getting in the classes. Very strange. It is actually, it is known that it is online classes not only difficult for you, difficult even teachers. When student doesn't respond, the student doesn't take interest, student doesn't listen. Despite the fact that all the conditions, we have to teach a class with full enthusiasm, with full spirit. It's really challenging for teachers also. So anyway, I will not, maybe I'm not qualified to give this kind of motivation things up. Guys, if you have any questions, let me know. Otherwise, we'll stop it here. No need to waste your time or waste my time. So I hope you all practice. Yeah, thank you. I hope you all practicing. Please practice. Otherwise, with this online system, you may get marks, you may get grades, but definitely you will not understand. You may say, I will later on, recordings are there, YouTube videos are there, I will learn it. So anyway, you have to learn it. You better learn now. And this software, whatever fluid mechanics, mass transfer, heat transfer, so many subjects, whatever calculations we have done, you could able to do in a very easy manner. So if you learn the software, that will make your life very easy. That's why I have spent time. Luckily, I got a lot of hours this semester compared to previous semester, so I could cover most of the topics. Last year I could not cover some of the topics to seniors, but this time I could cover almost all the topics there in this process. Okay, have a great day and see you next week. Thank you.
Thank you, sir.